To understand the behavior of Heusler and half-Heusler compounds, we first look at their construction. These are ternary intermetallic materials formed by combining three distinct metals in strict ratios, specifically 2:1:1 or 1:1:1. These materials are composed of metals and transition metals. However, the resulting alloy does not always act like a metal. In many cases, these combinations lock into non-magnetic semiconductors, topological insulators, or even superconductors. The choice of specific elements, whether titanium, cobalt, or antimony, is secondary to the exact geometry they form and the total number of valence electrons they contribute. This reference document outlines the predictive framework. It shows that if a half-Heusler compound reaches an exact count of 8 or 18 valence electrons, it forms a hybridization gap and functions as a semiconductor. We can see how this happens by deriving the chemical bonding model from first principles. We will trace the orbital math to show why 18 valence electrons force a metallic alloy to open a semiconducting band gap. The macroscopic behavior of these materials is a direct outcome of microscopic electron math. Adjusting the count by a single electron redefines the fundamental state of the matter. Before counting electrons, we need to establish the physical geometry that makes this possible. We must observe the internal architecture of a half-Heusler compound. This diagram illustrates the foundational layer. Two elements bond to form a covalent zinc blend structure at the 4A and 4C positions. Then, a third element is inserted into the vacant 4B octahedral holes. This addition creates three interpenetrating face-centered cubic sublattices, completing the half-Heusler architecture. By filling these specific tetrahedral voids, the geometry creates a dual-nature bonding environment. Directed covalent interactions between the zinc blend elements operate alongside undirected ionic interactions with the third element. These charge density distributions prove the dual bond nature. On the top left, pure silicon displays uniform, directed covalent bonds. On the bottom right, the titanium-cobalt-antimony half-Heusler shows modified covalent bonds. High electron density forms bridges between cobalt and antimony, while titanium remains isolated, interacting through ionic forces. Combining strong covalent pathways with localized ionic pockets breaks the structural symmetry of the crystal lattice. In solid-state physics, breaking crystalline symmetry is a requirement for an energy gap to form. In a standard metallic alloy, electronic states typically overlap and remain continuous. The interpenetrating sublattices in a half-Heusler compound force a break in that symmetry, creating the physical conditions necessary to split those states into separate bands. Now that the asymmetric geometry is set, we can shift to quantum chemistry to see how these energy states separate. This molecular orbital diagram charts the energy states of lithium, aluminum, silicon. First, aluminum and silicon atoms hybridize. Their atomic states split to form 4 lower bonding orbitals and 4 higher antibonding orbitals. Then, the electropositive lithium atom transfers its valence electron, leaving its empty state above the antibonding orbitals. This sequence shows what happens when we total the available valence electrons: 1 from lithium, 3 from aluminum, and 4 from silicon. They sum to exactly 8. Placing those 8 valence electrons into the compound completely fills the 4 lower bonding states in pairs. This leaves the high-energy antibonding states empty. The 8-electron rule is the exact mathematical volume of electrons required to fill the lattice's structural potential well, positioning the Fermi energy in a stable vacuum between the bands. This same logic applies to the transition metal half-Heuslers, but the presence of d orbitals alters the math. This diagram tracks the orbital derivation for titanium, cobalt, antimony. We start with the covalent interaction. Antimony's orbitals hybridize with cobalt's on occupied orbitals, forming bonding and antibonding states. Initially, cobalt's 3d orbitals remain isolated. In the second ionic phase, this cobalt-antimony substructure interacts with the titanium ion. Through octahedral splitting, the titanium 3d orbitals interact with the cobalt 3d orbitals. This generates new sets of double degenerate E and triple degenerate T2 orbitals, finalizing the energy map. This chart demonstrates the final electron count. When you add the valence electrons from titanium, cobalt, and antimony, you get exactly 18. They fill the energy architecture up to the Fermi energy line. 18 valence electrons perfectly occupy all available bonding states. The energy gap is preserved, and the compound stabilizes as a non-magnetic semiconductor. Consider what happens if we build a similar structure using elements that yield 17 or 19 valence electrons. 17 electrons leave bonding states incomplete, while 19 are forced into high-energy antibonding states. In both cases, structural stability fails, collapsing the energy gap. 18 valence electrons represents a hard structural limit. Moving to 19 electrons fills the vacant states above the gap, turning the semiconductor into a conductive magnetic metal. Applying this framework to full Heusler compounds requires a new calculation, because the crystal geometry is different. This comparison places the half-Heusler architecture alongside the full Heusler architecture. A fourth interpenetrating sublattice is added, inserting a second transition metal to fill the remaining tetrahedral holes. That additional transition metal alters the d orbital coupling equations. The interaction between these extra atomic states narrows the size of the potential energy gap. Because the architecture has expanded, the threshold to fill the bonding states changes. Full Heusler compounds require exactly 24 valence electrons to clear the gap and function as semiconductors. This 24-electron state is fragile. Because the energy gap is narrower than in 18-electron compounds, full Heuslers are vulnerable to crystallographic errors. If the material develops atomic disorder, atoms swap their designated lattice sites, disrupting the geometry required to maintain amorbital splits. Misaligned atoms inject an unintended density of states directly at the Fermi level. When the Fermi level is populated due to structural disorder, the semiconducting gap closes, allowing the material to conduct electricity and develop magnetic properties. The properties of Heusler compounds are a product of stoichiometric precision and perfect crystallographic execution. Their function is dictated by the geometry of the atomic lattice.